Hello students, let's start with the ranges of these three bands. Ultraviolet radiations stretch from 100 angstroms up to 4000 angstroms, that's 1 nanometer scale. Visible light sits comfortably between 4000 and 8000 angstroms, the rainbow we actually see. Infrared begins just beyond red, ranging from 8000 angstroms up to 10 to the power 7 angstroms, moving us into the realm of heat waves. So, think of visible light as the sandwich filling, with ultraviolet on one side and infrared on the other. Now, let's talk about what our eyes and skin notice. Ultraviolet is invisible, our eyes simply can't detect it. The same goes for infrared. Only visible light falls in the sweet spot for human vision. But when it comes to heating, ultraviolet produces no heating effect. Visible light produces a slight warming, and infrared gives a strong heating effect. That's why an infrared lamp keeps you warm in winter, while UV lamps don't heat the room but can cause chemical effects. Here's a fun one. How do these radiations treat photographic plates and fluorescent screens? Ultraviolet is super active. It blackens photographic plates and makes fluorescent materials like zinc sulfide glow. Visible light does affect photographic plates, but it doesn't cause fluorescence. Infrared? It does neither. That's why infrared cameras need special sensors rather than ordinary films. So the rule is simple: the higher the frequency, the greater the chemical punch. Now, let's talk biology. Ultraviolet rays can be hazardous. Prolonged exposure can cause skin cancer or burns. That's why sunscreen ads always mention UV protection. Visible light is our daily companion. It doesn't really harm the body under normal conditions. Infrared, on the other hand, is usually harmless, but prolonged high exposure can cause skin burns. Imagine standing too close to a bonfire. That's infrared at work. Let's now check who passes through what. Ultraviolet rays can sneak through quartz but are blocked by glass. That's why UV lamps often use quartz envelopes. Visible light passes happily through glass. That's the reason for transparent windows, lenses, and spectacles. Infrared can pass through rock salt but not glass, a little twist in material science. So if scientists want to study infrared, they use rock salt prisms instead of glass. Here's a calculation that shows why ultraviolet light is more dangerous than infrared. Let's compare their photon energies. For ultraviolet light at wavelength 200 nanometers, the energy per photon is given by the relation E equals hc divided by lambda. Substituting the values 6.63 times 10 to the power minus 34 multiplied by 3 times 10 to the power 8 divided by 200 times 10 to the power minus 9. The result comes out to about 9.9 times 10 to the power minus 19 joules. Now for infrared light at 2000 nanometers, the energy drops to about 9.9 times 10 to the power minus 20 joules, that's 10 times smaller. So ultraviolet photons carry nearly 10 times more energy than infrared photons. That's why ultraviolet is chemically active and hazardous, while infrared is relatively harmless. Let's do a quick recap, comparing ultraviolet, visible, and infrared radiations. Ultraviolet light ranges from 100 to 4000 angstroms. It is invisible to our eyes, causes no heating, but produces strong chemical effects, making it hazardous. Visible light ranges from 4000 to 8000 angstroms. This is the part of the spectrum we can see. It produces slight heating, is generally safe for the human body, and can pass easily through glass. Infrared light ranges from 8000 up to 10 to the power 7 angstroms. It is invisible, produces strong heating, and is safe at low levels. Infrared can pass through materials like rock salt. In short, the key differences between ultraviolet, visible, and infrared arise from their wavelength, frequency, photon energy, and transmission properties.